Okay, polyprotic acids. So polyprotic acids have 2 or more ionizable protons, and they ionize in successive steps. So here is an example: sulfurous acid, H2SO3. It has 2 hydrogen ions that can be removed. So the first one gets removed, and we have hydrogen ion and hydrogen sulfite ion, and this has a Ka of 1.6 times 10 to the minus 2. Small. And then removing the second hydrogen ion has a Ka of 6.8 times 10 to the minus 8, which is much, much smaller. So each step, each proton that's removed has its own acid dissociation constant, its own Ka. And the first one is going to have a higher Ka. The second one is going to be smaller. And if there's a third one, that's going to be even smaller. Because the first proton is leaving a neutral molecule. The second proton is leaving an anion. So we're taking a hydrogen ion, a cation, away from a negatively charged ion. That's going to be harder. And so this constant is lower, reflecting that this reaction stays more to the left than going to the right. Does that make sense? So here are some common polyprotic acids and their ionization constants. So there's a first ionization, second ionization, and a couple of them have a third ionization. So the first one up here is sulfuric acid. Well, sulfuric acid was one of the strong acids, right? It is strong in the ionization of the first hydrogen. So this will go to hydrogen sulfate completely. That's why this just says strong. But removing the hydrogen from hydrogen sulfate has this Ka value. Oxalic acid is diprotic. One of these comes off, then the other, and so you have the successive ionization constants. Here's sulfurous acid, similar to sulfuric acid, but one less oxygen, and the first ionization is also weak. Phosphoric acid and citric acid have 3 ionizable protons. Any questions?
Why isn't the Ka1 for phosphoric acid the same as Ka2 for sulfuric acid? Didn't you say that's what would happen?
Well, that's a good question. So why isn't this the same as that one? Because phosphorus is a different element.
No, the sulfurous acid.
Oh, why aren't these the same?
Yeah, because you said you took a hydrogen away from the sulfuric acid, that's what the number would be for. But isn't that what the sulfurous acid would be?
No, well, sulfurous acid only has 3 oxygens. And sulfuric acid has 4 oxygens. And it's the 4 oxygens that change the nature of how that hydrogen ion comes off. And like I said, that's going to show up later. Yeah.
So if they're like diprotic, or would it be like triprotic? So if we're like on a test or something, if we're told that it has 3.
Yeah, if it has
A's,
3,
would know that
it's triprotic. And I lied. I think I said that we were going to look at this in the in chapter 17, but I think it's coming up in this chapter. I'm just, I was falling asleep over my PowerPoint slides last night, and so I kind of got them muddled together. I finished chapter 16. 17, not so much. I do have time, yeah. Because I was panicking that we were supposed to be in next week, but we're not. So it's okay. So we can relax. Okay, finding the pH of polyprotic acid solutions. So it seems like this could be a lot more complicated, right? Because we've got these different possibilities. But the first Ka is much larger than the second or third. And so the amount of hydronium ion formed by that first step is much larger. And then the formation of that hydronium actually will inhibit the formation of hydronium in the second step. So we can generally treat these as if there's only one, if only the first step is going to contribute any hydronium ion. The only exception, well, the major exception, is if you have a dilute solution of sulfuric acid. In a dilute solution, you've got that first one coming off as a strong acid, and then you do have to consider the second one. So find the pH of a 0.050 molar carbonic acid solution. Well, what do we have going on here? Let's look at both of the steps. So we have H2CO3, and that's going to form hydrogen ions and hydrogen carbonate ions. And then the second step is the hydrogen carbonate ions losing a hydrogen ion and giving us carbonate ions. Oops, that's a 3. The first ionization has a larger Ka. It proceeds farther. It's producing hydrogen ions. In this equilibrium over here, if we add a bunch of hydrogen ions in here from this, that's going to reduce the amount of ionization that occurs there. So let's set up an ice table. So we're going to start with 0.050 molar H2CO3, and we're initially starting with essentially 0 of the hydrogen ion and 0 of the hydrogen carbonate ion. And then the reaction is going to go forward, and so we're going to lose some amount X, and we're going to gain an amount X and gain an amount X. So at equilibrium, we've got 0.050 minus X, and we've got X and X. And so Ka, this is Ka1, is going to equal X squared over 0.050 minus X. Now, we were doing stuff like that last week. If you're not understanding, please ask. So in order to find X, we need to know what the Ka value is. Well, we go look it up in the table. So Ka1 for carbonic acid, I'm going to write these on the board, 4.3 times 10 to the minus 7. And for the second one, it's 5.6 times 10 to the minus 11. So that's Ka1 and Ka2 for carbonic acid. So we go back to our problem here. And let's try the X is small approximation, because we have a small Ka here, and so that's probably going to be okay. OKA. That's what Canadians would say. Okay, eh? Sorry, mind is spinning out of control. This is 4.3 times 10 to the minus 7. So if we say that X is small, then we can just ignore that part right there. And so X is going to be the square root of 4.3 times 10 to the minus 7 times 0.05. So X is going to be 0.00015, or 1.5 times 10 to the minus 4. Is that small compared to this? Yeah, it is. Let's double check, divide by 0.05. Yeah, that's 0.29%. No problem. X is small. So this is X, and so that's going to give me the hydrogen ion concentration and the hydrogen carbonate ion concentration from the first ionization. Does that make sense? So then let's see what's going to happen over here. What would be a good way to do this? I think I need different colors. So what I'm going to put in here is we figured out that this and then is going to be 1.5 times 10 to the minus 4. And this one is 1.5 times 10 to the minus 4. And that one is still basically 0.05. So at equilibrium, we have these concentrations. So then if we look at this one over here, now we have a concentration for the HCO3. It's the 1.5 times 10 to the minus 4. Can we say that the hydrogen ion concentration is essentially 0? No, because we've already got 1.5 times 10 to the minus 4 molar hydrogen ion from the first ionization. So we should put that in here. Do we have to worry about the contribution of water? No, because that's 10 to the minus 7, and adding that on to 10 to the minus 4 is too small, doesn't matter. What's our initial concentration of carbonate ion? 0. Okay. Because this one is 0, the reaction can only go in the forward direction. So, bless you, we're going to lose X here, we're going to gain X there, and gain X here. So now we have 1.5 times 10 to the minus 4 minus X, and we have 1.4 times 10 to the minus 4 plus X, and then we have X. So Ka2 was 5.6 times 10 to the minus 11, and that's going to equal 1.5 times 10 to the minus 4 plus X times X divided by 1.5 times 10 to the minus 4 minus X. So I took these equilibrium expressions here, the product times the other product divided by the reactant. That's my equilibrium constant expression, and that equals this constant here. So if I do the X is small approximation, what happens? I get X being Ka, right? Because if I say, well, here adding X doesn't make any difference and subtracting X doesn't make any difference, then I have 1.5 times 10 to the minus 4 over itself, and those cancel out, and X equals 5.6 times 10 to the minus 4. So is that small relative to 1.5 times 10 to the minus 4? Yeah, it's crazy small.
Is it 5.6 times 10 to the negative 4 or negative 11?
It's 5.6 times 10 to the minus 11 is what Ka equals. The X's small approximation is going to cause these X's to go away. And then those numbers cancel out, and we end up with X being equal to 5.6 times 10 to the minus 11. So that would give us our molarity of carbonate ion. We don't care about that because we're looking for the pH. So the hydrogen ion concentration at equilibrium here, 1.5 times 10 to the minus 4 plus this crazy small number, doesn't matter. So the hydrogen ion concentration we end up with, we can do all this work, but we end up with the same concentration as just from looking at the first step. So hydrogen ion remains 1.5 times 10 to the minus 4. The question's asking for the pH. So we've got negative base 10 log of 1.5 times 10 to the minus 4. And it's 3.82.
Okay, back that up a little bit.
Mm-hmm.
How come we did, for the second one, how come we didn't use that H value? You know, you calculate the X and then like, you know, I just add it. How come you didn't use that one again? Yeah.
Well, so this is what I started with. You're okay with that, right? And then I said, okay, we're going to lose X from this one, we're going to gain X here, and we're going to gain X there. And so this is what the expressions would be. The X is small approximation says, well, X is so small that subtracting it from this number isn't going to make any difference. And it's so small that adding it to that number isn't going to make any difference. And so we simplify those terms. We can't say that this one is 0, that it's so small it doesn't matter, because that one's not added to anything. So we leave that one alone, but anywhere we're adding or subtracting x's, we're just going to make the x's go away. That is the x is small approximation. So then we solve this for that, and we end up with x being very small indeed. So if you add this to 1.5 times 10 to the minus 4, it doesn't matter.
Can you do the x small to get to the square root? Why isn't that at all? Just because it's 1.
That's a good question. Why did we've been doing square root of all of this stuff? Well, that's because when we do one like this, we started out with none of the products. And so then we end up with x squared in the numerator. Here we started out with a significant amount of one of the products. So we end up with that plus x, but that x goes away. Good question.
All right, so you have one h value there and another h value right there.
Uh-huh.
Could there ever be a case that they'll be different? And if they are, which one would you use?
Well, they can't really be different. So this is the reaction that happens first. And so I'm going to look at that, and that's going to give me an equilibrium concentration of hydrogen ions. Then that and this hydrogen carbonate ion can also react. We can have this ionization, and so I'm going to look at that after. And what we see from this is we actually didn't need to look at this at all because it didn't affect the pH at all. Because the contribution from the second ionization was so tiny, it didn't matter. But we're going to look at it here.
Just in case? Or?
Yeah, just to show you that it doesn't matter.
Oh, okay. So
Yeah.
we can just do it once and then...
Yeah, just do this.
All right.
So diprotic, triprotic acid, just do the first ionization, find the hydrogen ion concentration. You're done.
Okay.
Any other questions? Now this was the one that we said you got to watch out for this one, a dilute sulfuric acid solution. So dilute, the concentration's really low, and sulfuric acid, the first ionization is strong. So we do have to look at both of the things. So let's see what happens here. So we've got an initial concentration of sulfuric acid. So we've got H2SO4, and that's going to completely ionize, forming hydrogen ion and hydrogen sulfate ion. So if we're starting off with 0.0075 molar of the sulfuric acid, and this goes to completion, then what do we know about our concentration of hydrogen ion and hydrogen sulfate ion? It's the 0.0075, right? So this is all gone, and now we've got 0.0075 and 0.0075. We don't really need an ice table or anything. There's no Ka to look up. It goes to completion. So all of this is gone, and we've made this. Now we're going to look at this one losing its proton. So now we're going to have HSO4 minus, and this is weak, and so it's going to lose a hydrogen ion and form sulfate ion. So now we will make our ice table. And these are our initial concentrations. So the starting concentration for the hydrogen sulfate is 0.0075. And the starting concentration for the hydrogen ion is 0.0075. Starting concentration for sulfate would be 0. This is not where it's going to stay, but this is where we're starting. Okay? So we have nothing here. No reverse reaction can happen. It's got to go forward. So that means we're going to lose X here. We're going to gain X there and gain X here. And so we've got 0.0075 minus X and 0.0075 plus X. And then this one's X. Yes?
How do you know that the hydrogen concentration in the first step was 0.0075?
Because when this ionizes completely, I get one hydrogen ion for every one hydrogen sulfate ion that's formed. And so their concentrations have to be equal. Because it's like shoes. There's a left shoe and a right shoe.
Well, it's because our sulfuric acid is a strong acid. So
Yes. Because it's strong acid when it loses the first one. So this goes to completion. So all of the sulfuric acid is ionized into hydrogen ion and hydrogen sulfate ion.
So this isn't a left or right reaction.
That's right. It's not an equilibrium. It's just going one direction. It's a good thing to get straightened out. So that's where we got our starting numbers. And then down here, so we're doing our regular ice table thing. Can somebody look up the Ka for 4.2? 1.2 times 10 to the minus 2. Thank you. So that's Ka2 for sulfuric acid. That's the Ka for removing the second hydrogen ion. So that's going to be equal to 0.0075 plus X times X divided by 0.0075 minus X. My eraser's too fat. Let's try that again. It didn't look like a 2. I mean, it did look like a 2. It was a 7. I confused myself. So if we do the X's small approximation, we're going to have the same thing happen that happened in the previous example. We lose the plus X, we lose the minus X. These numbers cancel out. X ends up being 1.2 times 10 to the minus 2. Is that small relative to 0.0075? 7.5 times 10 to the minus 3? No, it's actually larger. So that's not going to work, right? So we cannot use X as small. So you can do it the hard way or you can use the solver. I'm using the solver. So I put 1.2 times 10 to the minus 2 on one side. And then I've got 0.0075 plus X times X divided by the quantity 0.0075 minus X and I'm going to solve. And so I got a value for X of 0.00385. Is that a valid root for this equation? Yeah, because if I take this and I subtract it from 0.0075, I don't end up with a negative concentration. So I'm trying to find the pH and the sulfate ion concentration. So I just determined that this is X. Well, the sulfate ion concentration is equal to X. So this is equal to the sulfate ion.
Did you put the 1.2 to the negative 2 on one side?
So on my 36X Pro, it gives me two sides. And I put the Ka value on one side and I put this other thing on the other side. If you've got a like an 84 or something where you have to have it equal to 0, then you would take this big mess here and just subtract the 1.2 times 10 to the minus 2.
I just keep getting a different number than you.
Okay, I think there probably is another root. So let's see if we can find that. I'm also getting negative 0.023.
I'm getting 0.001022.
So there might be an issue with your calculator and how you're putting the numbers in. You have to be really careful with parentheses and dividing and stuff here. It's so easy to get it just a smidge wrong. But there's the sulfate ion concentration. What's the hydrogen ion concentration? Well, it's this guy right here. It's what I started with from the complete ionization of the first one, plus the X that I just found. So 0.01135. And then negative log of that. Probably 1.95. So pH equals 1.95. That is a 3.5, yes. So in 1A, we're always talking about significant figures, significant figures, significant figures. And so far in 1B, we've just been really kind of sloppy with them, right? Don't get too sloppy. Too sloppy is rounding things off to one significant figure. Some of you did that on experiment 15A, and you ended up with incorrect mole fractions because you rounded way too much. So it's always better to keep a couple extra digits, and then you can round it off at the end. I'm not going to try to hammer you on sig figs in this class, but if you round off too much and end up with the wrong answer, it's just going to be the wrong answer. If you carry too many, you're not going to end up with the wrong answer. So we are playing fast and loose with the sig figs, which makes me crazy, but we'll get through it. Any questions? So in this case, with the dilute H2SO4, we can't just look at the first one and say, oh, well, it's going to be 0.0075. Because there was further ionization, and so the hydrogen ion concentration was significantly higher. And so we did have to look at both of them. But with most diprotic, triprotic acids, you just look at the first ionization. Finding the concentration of the anions. So what if we want to know what the concentration of the anions are? So here we have a generic diprotic acid. We're just putting in X for an element. So H2X, we're going to have a first ionization, and then we've got the second ionization, and we've got our Kas. So if we want to know what the middle one is, where we've lost one of the protons, you're going to calculate the hydronium ion concentration just like we did for a weak monoprotic acid. And the HX concentration is the same. Because for every hydrogen or hydronium ion you get, you're going to get one of these. And as before, the second ionization, X ends up being small, and so it doesn't change the HX minus concentration. Now, if you want to know what the X2 minus concentration is, then you're going to do the first step, find X minus and H3O plus, and plug them in here as your starting values, and do the calculation again. X is small, but now X is the concentration of that ion that you want. And so it's going to be really small, but that's how you find it. Let's do an example, and hopefully this will make a little more sense. So this is the same one we did in 1617. But now instead of just finding the pH of this weak diprotic acid solution, they want to know what's the carbonate ion concentration. So H2CO3 in equilibrium with hydrogen and, hydrogen carbonate ions. Is it this one? Are these the right Kas? Or was that a different acid? Those are the right ones? Okay, cool. So the 0.05 to start out with, 0 and 0. I'm going to run through this quickly because we already did this. We're going to lose X there, gain X here, gain X there. At equilibrium, we've got 0.05 minus X. We've got X and we've got X. And so our Ka value, 4.3 times 10 to the minus 7 equals X squared over 0.050 minus X. We can do the X's small approximation. So we end up with X being equal to the square root of Ka times that initial concentration. 1.5 times 10 to the minus 4. That's sounding familiar. We're trying to find the carbonate ion concentration. So now we'll take that hydrogen carbonate and have that ionize and do another ice table for this one. So we have now figured out what the equilibrium concentrations are from the first ionization. This one isn't showing up, so we're going to ignore that one, but these are both X. And so we got 1.5 times 10 to the minus 4 and 1.5 times 10 to the minus 4 and the 0. And on the previous slide, this is what it was saying. If you're trying to find the anion formed by ionizing one proton, it's going to end up being the same as the hydrogen ion concentration. But we're looking for the one where we've lost both the protons. So again, we've got minus X plus X and plus X. And our equilibrium, our Ka is 5.6 times 10 to the minus 11. And that equals those products, 1.5 times 10 to the minus 4 minus X, plus X, times X, divided by that. And if we use the X's small approximation, X ends up being 5.6 times 10 to the minus 11. Because X is small says, well, so adding X and subtracting X doesn't matter. It's too small relative to the 1.5 times 10 to the minus 4. And then these numbers cancel out, and we have X equals Ka. So the carbonate ion concentration is going to equal 5.6 times 10 to the minus 11. Any questions? Yeah.
So for these, usually the base without any hydrogens will have the same as the Ka2?
Yeah, this will generally end up being the same concentration as Ka2. Yeah. Which is really, really small. And most of the time, it's like so small that we're like, yeah, it doesn't matter at all.
Kind of raise the question. Let's say we know if it's negative log that, will that be the pH of that or will that be the pOH of
Of this?
Yeah. Like,
Well, we could find the PCO3 of it.
oh, never mind. Yeah.
Yeah, we could definitely do that. Any other questions? So here we're looking at, I think this is citric acid. Don't quote me on that. Here we have diprotic acid. It dissociates. We get hydronium ion being formed. When the second one dissociates, we also get hydronium ion being formed. This one is so small relative to that one that when we add them together, it's the same. It's like throwing an orange on top of a semi-truck full of oranges. Yeah, you added mass to that, but the whole thing is so huge that little thing you did doesn't matter at all. So the amount of hydronium ion from the second step is insignificant, and the concentration of that X2 minus ion from the weak diprotic acid is going to be equal to Ka2 whenever X's small approximation is valid, which it usually is, yeah. But we do have to, qualify everything. It's like, if that's valid, then this is true.
And the only reason that would change is the dilute.
Yeah, if our acid solution was very dilute, where now our concentrations are down on the order of the Kas, then yeah, we have to think about it, and X is not going to be small, relative.
And you would let us know, like, if the solution that we're calculating for is dilute or not.
Well, you're given the initial concentration, right? And so you can see if it's dilute. You should always, anytime you use X's small approximation, you should always check.
Okay.
Take the X value you got and divide it by the number you were going to add or subtract it to.
And if it's not, then...
If it's not, then you have to do the solver thing and find out what X really is.